The topic is boundary conditions. Till now we consider the electric field in a homogeneous medium, means we consider the electric field in dielectric only or conductor only or free space only, means we consider electric field only in one medium, means homogeneous medium. Now if we talk about the electric field in a region consists of two different media, means it is a combination of two different media such as dielectric-dielectric, conductor-dielectric, and third is conductor and free space. So we have to find the condition that the field must satisfy at the interface of two different media, and these conditions are called boundary conditions. Now these conditions are very helpful in determining the fields. Fields may be electric field capital E vector and electric flux density capital D vector. Okay, means these conditions are helpful in determining the fields. If the fields on one side of the boundary is known, then with the help of these known boundaries in the one region we can determine the fields in the other region of the boundary. So these are the boundary conditions, means within a boundary if condition of one region is known, the other fields can be determined with the help of the known fields. So here to determine the boundary conditions we use Maxwell's equation. So here we use two Maxwell's equation. First is closed line integral E dot dl, that is equals to 0, and second is surface integration closed surface integral D dot ds equals to q enclosed. So we use two Maxwell's equation. In first one we use a field that is electric field E vector, and second we use electric flux density capital D vector. So here we use two fields, E field, electric field E and electric flux density D. We take electric field in a closed path, and second is we take a electric flux density D in a closed surface. So we use these two equations to determine the boundary conditions. Now the first step is we divide it into two components. That components are called orthogonal components. For example, electric field has two components. First is tangential and second is normal. Tangential is denoted by E suffix t and normal is denoted by E suffix n. Similarly, electric flux density D also break into two components, tangential component, normal component. So we can say that the field having a summation of tangential component and normal component. So the first interface is dielectric-dielectric boundary condition. So here we use a dielectric-dielectric boundary. Here we take a two region, region 1 having dielectric constant epsilon 1 and region 2 having a dielectric constant epsilon 2. Here dielectric constant is epsilon r, usually epsilon r1 and epsilon r2 in region 2. So we determine the boundary condition by using first Maxwell equation, that is integration E dot dl, that is equals to 0. Now we take an electric field. So here we directed the electric field from region 1 to region 2. In region 1 we call electric field E1 and in region 2 we call it E2. Now similarly the E1 has two components. It is a combination of two components, normal component and tangential component, denoted by 1n and tangential is E1t. Similarly the E2 has also two components, normal component and tangential component. Now after that, by using the first Maxwell equation, that is closed line integral. So for this we draw a closed path, assumed closed path. That closed path is of rectangular one. In this, half of the path is in region 1 and half of the path is in region 2. Now we name the path A, B, C and D. So this closed path is divided into 4 paths. First is AB path, second BC, and third is CD, and fourth is DA path. Now this closed path has some dimension. We call it delta W width and delta H height. So we gives this arrangement here. So now we apply E dot dl within a closed path. So for our convenience we take a magnitude part of field, magnitude part of E1 and E2. Now we start from point A and close it to the same point A. So the first path is AB path. Now from figure here we see that the direction of AB path is in the direction of tangential component of E1. So according to this Maxwell's equation, that is E dot dl. Here E is E1t and dl, that is a path distance, that is delta W. So first path having value E1t into delta W. Similarly the second path that is BC path, that is half within region 1 and half within region 2. So here we consider the height delta H. So half of the height is within region 1. So in this case the direction of BC, that is normal towards. So within a region 1, this is normal E1n into half height, that is delta H by 2, plus half in region 2, that is delta H by 2, and this is also in a normal, but here the normal component is E2n component because this is in region 2. Now the third path, that is CD path. Now here we see that CD path having a direction that is opposite to the tangential component of E2. So here we take a minus E2t delta W. Delta W is the width, that is length of this path. Now again, while moving from D to A, we move half in region 2 plus half in region 1. So again delta H by 2, we use delta H by 2. But here we see from figure that this direction is again normal direction but in opposite direction. So again we take a minus term here. Here minus term is E2n into delta H by 2 and minus E1n delta H by 2 equals to 0. Equals to 0 is from Maxwell's equation. So after cancelling some terms, we get E1t minus E2t within bracket delta W equals to 0. Now if we assume that the dimensions are of very small, that is delta H tends to 0, then delta W is also equals to 0. So in this case E1t equals to E2t. So from here, from this equation we see that the tangential component of electric field, that is E1t and E2t is equal, means it is the tangential component of electric field is constant, is continuous across the boundary. So in case of electric field, the tangential component is continuous for dielectric-dielectric boundary. Similarly, since we know that electric flux density D equals to epsilon E, so from here again electric flux density is break into tangential normal component. So in terms of electric flux density D, E1T equals to D1T upon epsilon 1 and E2T equals to D2T upon epsilon 2. After putting these two terms in equation 1, we get D1T upon epsilon 1 equals to D2T upon epsilon 2. So from equation 2, we see that the tangential component of D is not continuous. It depends upon the value of epsilon 1 and epsilon 2. So from here, the tangential component of electric field is continuous, while the tangential component of electric flux density D is not continuous at the dielectric-dielectric boundary. Similarly, we apply the second Maxwell's equation, that is closed surface integration D dot ds, that is equals to Q enclosed. Here we take a field that is electric flux density D. So we directed the electric flux density D from region 1 to region 2 and name it D1 vector and D2 vector. Similarly, D1 having two component, normal and tangential, and also the D2 has a normal and tangential. Now the second step is for the application of this Maxwell equation, that is a closed surface integration, we take a closed surface. So here we take a closed surface, and in this case we take a closed cylinder. Half of the cylinder is within region 1 and half of the cylinder is within region 2. Now this closed cylinder have a surface charge density rho s and its cross sectional area is delta s. This cylinder has total height of delta h, means half of the delta h is within region 1 and half of the delta h is within region 2. Now we apply a Maxwell equation, that is closed surface integration D dot ds equals to Q enclosed. So here we see that this cylinder has three surfaces, top surface, bottom and a curved surface. So we apply a closed surface integration, that is divided into three surfaces. Surface integration for the top, surface integration for the bottom and surface integration for the side. Here the surface integration of the curved surface, that is the side one, is 0. This is due to the symmetry of this cylinder. As we move on the surface of the cylinder, we have the symmetry. Due to that symmetry, if we take a surface integration, it tends to 0. So we cancel this term. So the remaining part is surface integration of top and surface integration of bottom. Now the bottom surface has a normal direction, means the normal direction, that is towards normal component of D2, that is D2n, and the bottom surface of this cylinder is again normal direction, but in this case this normal direction is opposite to the given one, dn1. So after taking these two terms, surface integration of top and bottom, we get d2n into delta s minus d1n into delta s, because here d1n, normal component of the bottom surface, is opposite to d1n and equals to q enclosed. Here as we take a surface charge density rho s, and we know that the surface charge density rho s equals to q upon surface area. So here q enclosed in terms of surface charge density is rho s into delta s. So after taking common delta s, it is cancelled and we get d2n minus d1n equals to rho s. We take care that the electric flux density D is directed from region 1 to region 2. If the electric flux density is directed from region 2 to region 1, then this third equation is applied accordingly. Means this term d1n minus d2n equals to this. So we take care for this, the directed. Now we note some point. If the surface has no free charge, that is rho s equals to 0. If there is no charge at the boundary, that is rho s equals to 0. In this case, d1n equals to d2n. So in this case, the normal component of electric flux density is continuous across the boundary. And we know that d equals to epsilon e. So in this case, epsilon 1 e1n equals to epsilon 2 e2n. So in this case, we see that from equation 5, the normal component of electric field is not continuous at the boundary. It depends upon epsilon 1 and epsilon 2. Now, there is a special case. The boundary condition can be used to determine the refraction of the electric field across the interface. Means, with the help of these boundary conditions, we can also determine the refraction of the field. It may be electric field or electric flux density. Now, according to our continuous boundary condition, that is, tangential component of E is continuous at the boundary. Also, the normal component of D is continuous at the boundary. So, we take these two continuous boundary conditions, and from figure, we see that the tangential component of E in terms of theta. So, here we take a refraction case. As directed from region 1 to region 2. In region 1, the field make an angle theta 1 with the normal, and in region 2, the fields make angle theta 2 with the normal. So here from this figure, even t in terms of theta can be written in terms of sine, and d1n in terms of theta can be written in terms of cos. So after knowing these terms, these continuous boundary conditions, and dividing these two terms, 1 and 2 equation, we get a law, that is tan theta 1 upon tan theta 2 equals to epsilon r1 upon epsilon r2. That is called a law of refraction of the electric field at the boundary that is free of charge. If the boundary is free of charge, then we can apply the law of refraction to determine the refraction. Next boundary condition is conductor-dielectric boundary condition. Here we take two regions. First region is conductor and second is dielectric. So in first region we consider a conductor, that is a perfect conductor, and we know that in a perfect conductor electric field intensity E is 0 since conductivity is infinite. Example of some perfect conductor is copper and silver. So we know this condition for the conductor. And in region 2 we consider a dielectric. So here we take a dielectric having epsilon, that is equals to epsilon naught into epsilon r. So again we apply an Maxwell's equation. First is integration E dot dl equals to 0 and second is integration D dot ds equals to q enclosed. So since there is no electric field within a perfect conductor, so there is no normal or tangential component, but in case of dielectric we represent the electric field in terms of tangential and normal components. Now for first Maxwell equation we consider a closed path similar to the dielectric-dielectric boundary conditions. So after applying this equation, that is in path AB there is no field, so 0 into delta W. In towards the path BC, now toward path BC, half of the path is within region 1, that is within region perfect conductor, so delta H by 2 into 0, and half of this path is within region 2, but in this case there is an electric field, that is normal component, that is En dot delta H by 2, dot means multiply En into delta H by 2. In third path, that is CD path, now this path is opposite to the tangential component of E. So it is minus ET into delta W. Delta W is the width of this CD path. Again, while moving from D to A, it is in normal direction but opposite to the normal component of E. Half of this in region 2, so it is En into delta H by 2, but half of dA within region 1, that is within perfect conductor, there is again no electric field, so it is 0 into delta H by 2. So within a perfect conductor, the E dot dl term is 0, and there is a cancellation of normal component, half of the height, that is En delta H by 2, and here minus En delta H by 2 is cancelled. We get only Et delta W equals to 0. So the tangential component of E is equals to 0 after assuming that delta S tends to 0. So in conductor dielectric boundary, the tangential component is 0. Now in case of second Maxwell equation, that is D dot ds equals to Q enclosed. Similarly, since in region 1 it is a perfect conductor, electric field E and D is 0, and in region 2 we represent the electric field density D in terms of tangential and normal component. So for this Maxwell equation we take a closed surface, and here we take a closed surface, that is cylinder having a surface charge density rho s. Now again there is a this cylinder has a three surfaces, top, bottom and curve, and curve have a symmetry, so the integration is again 0. We have top and bottom surface integration, that is equals to Q enclosed. So here we know that in region 1, that is bottom surface has normal component, but here D is 0, so 0 into ds with minus sign, and in top its direction is towards normal direction of dn. So after putting these values, and we know that Q can be written in terms of surface charge density rho s, that is rho s into delta s. After cancelling the delta s term, we get normal component of D equals to surface charge density. So in case of conductor dielectric boundary condition, the tangential component of E is 0, while the normal component of D is equals to surface charge density. And since D equals to epsilon E and epsilon equals to epsilon naught epsilon r, so after this it is equals to rho s. Now the third interface is conductor free space boundary. Here again we take a conductor is a perfect one, that is E equals to 0, and the second medium, that is a space, free space. In case of free space, the relative permittivity epsilon r equals to 1. So the tangential component of electric field density D equals to epsilon naught E suffix T. here epsilon r equals to 1 and that is equals to 0 since the tangential component of E is 0. While the normal component of D is again epsilon naught En, that is equals to rho s. So we can say that the electric field E must be external to the conductor and that is normal to its surface only. And there is only normal component, while the tangential component of D is always 0.